someone have supercomputer in Delhi and you can access from IIIT City. So platform also you can use and software. So all these things are having sharing environment. So there is a different kind of reason behind this. It has on-demand services, broad network access, rapid elasticity, and outsourced IT management and resource pooling. These are the reasons why we need to see cloud. But any technology comes with challenges. These are the challenges which we have categorized. This is categorized by our research team, but we can get more challenges than this. So I'm not claiming that only these challenges are possible. Some more problems are also there, but this is major challenges you can see started from resource distribution to compliances. Some of the problems we are fixing in our research. So the first challenge we take it like resource utilization. Whenever we go for conventional resource utilization, to take this example, we have 5 servers, server 1 to server 5, and every server has different type of uses. So server 1, for example, memory utilization is 30%, CPU utilization is 20%. So both 50%, so 50% is used, 50% is unused. But you can see this guy, server 4, this place, 90% is used and 10% is unused. It's overload. And underload, it's like memory and CPU both are only 25%, rest 75% are not utilized. So what you can see, something like a better consequence. If cloud is a human being like me, and I'm taking a lot of food, like overload, someone is taking less number of food, underload, both are having dangerous situation. And because of overload and underload situation, we get like power excess consumption, resource wastage, frequent VM migration, increased SLA violation, performance degradation. And this diagram is simple, but the problem is very complicated. You can imagine billions of users are just requesting for one memory. You know, cloud data centers. Unfortunately, our country is not having a single cloud data center available for public. So cloud data center is something like you can see the area of your city. And they have like millions of servers are active. And they are underload. So what happened because of this? Once they are underload means they are taking a lot of power. Resources are wasted. And because of this, SLA violation means service level agreement. So deal these challenges, we need to effectively manage the resource and predict workload. And ladies and gentlemen, resource management is not the problem of cloud environment only. It's the problem of social structure. You can imagine like thousand years to manage the resources effectively among common people. You can have a question. If God has given birth to everyone, why someone is rich and why someone is poor? Why not we have efficient or effective resource management? Why not money is equally distributed? Because resources are developed for everyone, not only for America or from England, right? For everyone, but we can't. And once you can think that way, then immediately you can grab this problem. So for this effective resource management, the first point is you have to predict workload. You have to predict workload, then only you can manage resources effectively. Means, you know, tomorrow you need 10 servers. So today you are ready with 10 servers. Prediction. Another one point I want to highlight here is so that you can track quickly. For example, I have 100 rupees and a father has 100 rupees. He has 4 kids and he has to distribute effectively. And what is the answer? 25 rupees each. So you can say effective distribution. But it's not. It never happened. Because you can imagine out of 4 brothers, 1 brother, father knows that he can misuse the money. So better not to give money to him. So distribution is 0, 33, 33, 33. Again, father knows that one person is very smart. If I give 25 rupees, by evening he can make it 50 rupees. So maybe that fellow will get 50 rupees, one person gets 0 rupees, and between these 2 people get 25, 25. And that's the effective management is used by God today. Therefore, you can see some countries very rich, they are having. So equal distribution is not only efficient resource management. Keep this point, and the reason I will tell you later. So for prediction, whenever we go for prediction, only one objective we have for prediction. We need 100% prediction. And for this, you know what is going to happen tomorrow. It's a very big question. Therefore, I said, even it is the cloud environment I'm using, but it's not only for cloud, for everywhere. For share market, you want to predict. For election result, you want to predict. I'm going to die tomorrow or not, also you want to go predict. So this workload prediction we do, and then after that we go for management. So we applied machine learning techniques for prediction. And why machine learning technique, I'll tell you later. Why not some other technique? So for this, we did some literature survey, all based on machine learning technique. And the reason is very clear, because since this data we are dealing with like huge number of users, we have millions, billions users we are having, and for them, the statistical analysis fail. We need some kind of machine generated, and machine learning is the best, like train the data and then we can get it. So we did some kind of literature survey, and I always suggest my all the audience that please read this literature survey. This literature survey paper we publish in IIIT Transaction and Cloud Computing. Even survey paper we publish in Transaction and Cloud Computing, so you can imagine what will be the quality of this. So we categorize, and you know this categorization was very, very difficult. This categorization belongs to us. You can challenge, I don't mind. So evolutionary learning, deep learning, hybrid learning, ensemble learning, and finally, our group proposed quantum learning, and name is given equivalent. So this is our workload prediction taxonomy. So for prediction, you apply machine learning, deep learning, statistical analysis, anything you apply. What is the target? The target is our prediction should be 100%, right? That is only one target you should have. Maybe computational complexity is more or less, it's okay, but prediction accuracy should be 100%. And for that, after this, we have some kind of sibling parameters. So that sibling parameters we calculated. The second part is, once prediction is performed, then after that we have to distribute. And for distribution, I gave a simple example that 100 rupees is going to distribute among 4 people. So 25 rupees each you can give. But if the father knows that this guy is not smart, then he will distribute differently. But take another example, that the same father, if there is a food distribution, chapati distribution, there is a 4 chapati. Sure, he is going to distribute 1, 1, 1, right? Even the kid is, kuch bhi hoga, he should eat basically. So whenever we go for distribution, we go for different level. Application level, virtual machine level, physical machine level, and all. And for application level, you know that some places we apply first input, first output. Some places we apply last input and first output, and the difference is just opposite. One one method say that who come first will get first. Another method say that who come last will get first. There is a reason behind this. So after this, we find it our research gap. After all the literature survey and the research gap in nutshell, the problem is very, very common problem. Prediction accuracy is not potent and durable with respect to changing workload, because this place workload is it's in million, and you can take the best example is Twitter. You know in 1 second how many tweets? In 1 second how many tweets? Sometimes it goes to million in 1 second, and that tweet is what? Even one tweet required some kind of hardware, some kind of saving things, some data, and all these things you have to manage. Like Facebook, you can see. These are basically used by common people, but other cases you can see, like credit card. Credit card data is also transferring in distributed environment. That places security is also placed in the picture. So these are some kind of research gap we find, and then we produce the solution. This is the first solution proposed by our group, quantum machine learning models for workload prediction. So this quantum machine learning model we proposed, we applied some kind of training algorithm from our side, didn't use existing one. Since I am from electronics guy, so Thoda quantum, I use some kind of weights and all from my side, and then you proceed. So for prediction, the basic concept we start from there that we need to use historical information for any kind of prediction in the world. Either use machine learning or statistical analysis. First of all, you have to do historical information. So this historical information is taken care by cloud data set. And then after this, the workload we have, and we have to normalize. So normalization is a very common practice in mathematics and computer science, because whenever we get the data, after that we do some kind of normalization. Something like average, you calculate the average, also a kind of normalization. But you consider, if one guy has $100 and another person has $1, and you take average becomes $55, but it's not. Because one fellow has only $1 and you average that, oh, he's having $55. So average is not sufficient, therefore mean mode is not sufficient. So different type of mathematical parameters are introduced by researcher for normalization. So I don't want to go in that. This place also you can do research. After that, machine learning, 3 categories are always there. That category is training, validation, and testing. So this place we apply. So see our contribution for training. We have applied equivalent, evolutionary quantum neural network. So first of all, we applied quantum. So from bit to qubit generation, we applied different kind of gate, and then went with existing algorithm evolutionary, because we were not interested to do so many experiments. So first we went through evolutionary. After that, once we got paper accepted in transaction, then we changed this algorithm like black hole theory, Indian wedding system, Indian democracy. This kind of training data we did. So from bit to qubit generation we did, and proceed for this. So after that, rest is same. Rest is all are trivial here. Once you train the data, then test, then validate, and predicted output you put to the load balancing part. So, for example, before going for any management, first we predict. And if our prediction is, for example, 100%, then we are very happy. After that, we can use our management effectively. So this is our evolutionary quantum neural network. So this diagram you can see, the tricky part is this place, qubit neurons. Now neurons are in qubit form, not in bit form. So from bit to qubit generation, there are so many ways. And this bit to qubit, we introduce our gates, then after that weights, then apply. So you can see for data pre-processing, I told you, it's like normalization of data. Everyone used to do. You want to play with the data, you want to train the data, first of all, you do normalization. Average nikalo, kuch bhi nikalo, something you need, or you don't do anything, also sufficient. So normalization, we did very nice things, very simple. You can see D, particular data is subtracted by minimum value and divided by maximum, difference between maximum and minimum. This place, also you can do the experiment. You can just apply something else, see this accuracy of our prediction is improving or decreasing, you can just check it. But this one, as a mathematician, if someone is sitting, can feel that difference between minimum and maximum is denominator and divided by difference between original value and minimum value. Some places you can apply difference between minimum, not minimum, maximum one. DI minus Dmax also you can take it. So you can get more accuracy. So input layer, after this qubit, you have to apply rotational effect. And you know, bit value, how it works, it is between 0 and 1. So whenever you take the data between 0 and 1, and once you transform into quantum, it's a rotation. So it can be any value between 0 to 1. Therefore, you can see this rotation effect by pi by 2 we applied, and then data is multiplied by pi by 2. And after this hidden layer, we applied C0 gate. So C0 gate is the property, you can see C0 gate effect. C0 gate is basically the quantum gate. It's the basic, I think, most fundamental gate of quantum is C0. And best example is, if you have AND operation, and when I say that the value is 1, output is 1, can you guess what is the input? If AND gate output is 1, then what is the input? All 1. All 1. But when I say what is output is 0, then what is input? Anything. Means output cannot guess input. But once you go for NOT gate, output is 1, then input is 0. Output is 0, then input is 1. So quantum gates, the first property is from output you can guess input. And conventional gates, not. So we applied here C0 gate here, C0 gate effect as an activation function, because for training, SVM use different kind of gates, different kind of fitness function use. And what you do basically, you just change your activation function. And our output layer, we applied C0 gate and we proceed. So after doing all these things, there are so many places which you can do as a researcher. Therefore, I'm saying that you see the where you can do the first part, you can do the contribution, normalization place. Whenever we are normalizing the data, this place you can do the experiment. And no, this place, I don't want to normalize like this. You can have different mathematics to normalize. The second place, during activation function, selection of activation function, you may not use C0 gate. You can use different kind of gate, Hadamard gate, Toffoli gate, Franklin gate, because these gates are also quantum image. So then after this, we produce another gate. You can see quantum black hole Hadamard neural network. And for training, we use evolutionary network. This case, instead of C0 gate, we applied Hadamard gate. You can see this case. H Hadamard quantum neural network. And for training, instead of evolutionary algorithm, we applied black hole theory. Black hole theory, you know that proposed by Stephen Hawking. And just now, I think 97 someone proved that okay, it is correct, and the black hole theory is very close to Indian democracy. Like Indian democracy, how it works? First you select MLA, and that MLA selects CM, right? Or PM is selected by member of parliament. Means CM doesn't belong to you. CM belongs to MLAs. American system is different. Everyone is contributing to select the president. Therefore, once counting goes for president in America, we need a lot of time. But our case, what happened? Since the number of data are more, when I said that we are dealing with billion numbers, so if you are getting one leader is difficult. So you just start getting local leaders. And that local leaders are going to select global leader. We applied black hole theory. And this paper, किस्मत ठीक नहीं है इस पेपर की, still 3 साल से under revision है. So I'm not showing the result of this. But this model I proposed, I presented in Imperial College London, and people were very happy to see this diagram. You know, one guy saying, "Kaise banaya ho?" And I told that that's okay, no, this is a secret. But we have this result. So after doing this, what is our result? That one I want to tell you, show you. We have taken the result from NASA and Saskatchewan. NASA is the standard benchmark. So in this case, you can see this pink color. Pink color belongs to our method, and rest or sorry, this red color equivalent, this one, and this others are different methods. All are basically published in recently published in transaction. So everywhere our prediction is getting better. So this prediction is getting better, and conclusion is better means 100% prediction to kabhi nahi hoga. Never ever. So only thing is that your error is less. So for example, like this place, our prediction accuracy error is reduced by 90% close. Another one is C2, this closer to actual value. Now you can see the red one is predicted value and black one is actual value. So whatever we predicted, you can see all closer. Rest graphs, rest methods are basically very far. And the reason is, theoretical reason is, कुछ लोग एनालॉग के बैठे होंगे यहाँ पे. Whenever we go for 0 and 1, the point is 0 and 1 is for voltage form is okay, but it's a range basically. So for example, like you say the 5 volt is 1. What happened in 4.9? 4.9 is basically become 0. So for electrical circuit is okay, like Cloud 7 proved that okay, 4.9 light is on, but it's a data. Data is not like this. Someone has 49 rupees and someone has 50 rupees. So what you are saying, 49 rupees who has is a poor guy and 50 rupees is a rich guy. But it's not. Therefore, whenever we apply data based on, technique based on, classical bits, all are basically far away from it. So quantum gives accurate result, but there is a problem. The problem is once you go for conversion with the quantum, it is going to take a lot of time. The time is there. And it is very clear, since we have a lot of hardware, rich hardware, we have supercomputers and all, then we claim our accuracy is better, but we are taking more time. We accept that we are taking more time, and time is manageable because it is a kind of offline exercise. So we can bear with this. Again, you can see the prediction accuracy improved by 25 to 95%. Some places it is data, 95%, some like 22 to 75.12%, and all this data we have taken. And these work are basically, the first paper was in 2021, transaction on parallel and distributed computing. And we were very much worried because quantum lot of machine learning algorithms are available in market. तो आप डेटा डालो, क्लोज करके रिजल्ट निकाल के दे देगा. But the point was, what was your contribution? Because once you go in good journal, they always ask for civil engineering is okay, mechanical engineering okay, but for computer scientists, what is the research part from us? Once data injected and run in the quantum, like, and then, so we were very happy that we convinced these things. And still I feel like if we could have big names in our group, we can do much better. So another, like so many papers with the quantum we have submitted, and we are working well. Today morning, we met with one of our friend and we just talking about explainable. So हम लोग explainable quantum पे जा रहे हैं. And let us see that कहाँ तक हम लोगों को we are going to get success or not. So we are going to apply our own theory, own training algorithm, and देखेंगे उसको explainable कर पाएंगे तो ठीक है. अब कोई मिले student को करें. The second part is, this is the first part of my talk. The second part is data privacy. In quantum, in the cloud, the major challenge is distributed environment. We are not sure that once we publish our picture in Facebook, picture is misused or not. And for your information, 2021, I read a news in this. Maximum penalty in the world was related to data privacy. One user had the cloud environment, data was leaked, and he claimed that maximum amount in the history. And you can see this one statistics we have. Now everyone moving to the cloud. After cyber physical system and Internet of Things, I will show the slide. Bina cloud ke kuch nahi ho. So whenever we are going to develop more security technique, the fraud should reduce, but it is not happening. The frauds are increasing. You can see 2021 more. But the point is it should decrease because more people are using cloud. It means researchers should focus to preserve their data, but unfortunately it is not happening. Second part is, you can see, whenever we are going to business, 55% people are saying my data should be secure. Even we get late, delay, time, money, power, they don't care. And if you go, really it happens. For example, I'm going to travel from here to airport. What is my first concern? The first concern is not to reach on time, reach there alive. The first concern. So therefore security. And therefore, as long as data is in my computer, I'm very happy, no problem. But once the data move to distributed environment, I should be worried that my data is private or not. Therefore, this data privacy and security is an evergreen problem. Anytime you can use. And what we did, we applied some kind of like technique to preserve, and what the idea we got it. Whatever I saw in my village 30 years back. My one auntie was there, she was alone. So when she was going to visit any relative, all the gold, she was putting in somehow with bhoose ke dher mein. I don't know how to call bhoose. like this where they put tidy field, they put it somewhere. Something like this hiding. That one was a kind of data privacy. So people were doing that kind of concept. I applied here. I will tell you later. So we did some kind of survey. And survey like data security is always having two parts. The first part is privacy, and second part is breach detection. And all cryptography, people say that I'm working data security, but not. They work in privacy because once the key is exposed, data is out. So what they are doing, cryptography, there's so many techniques here. AES, GM, RSA, DES, access control, differential privacy, all anonymization. These are basically privacy. Anonymization is very common. Like we talk about someone, but we don't tell the name. So a lot of data are floating to the distributed environment. Our credit card, how it works. This only 9 digits are moving through distributed environment. Only your name is taken out. Only your name is not there. So I'm talking about my friend, maybe I'm talking about Rakesh and saying that the person is like this, is like this, like this. Only I don't tell his name. It's anonymization. And that is very common. That first few tuples, first few attributes you have taken out, and data is moving throughout the environment. But now people are more smart. They are guessing, they are combining. So these are 4 major categories for privacy. The second part is breach detection. And this place we work more. Like what happened if the data is leaked? So we detect the malicious user. Who leaked the data? And I'll tell you guys, who leaked the data is not very easy job. Still, you know that so many murders in our world history, so many stolen documents, we don't know who did. We don't know who did. And therefore, I say that it's not an easy job to detect the leaker. We applied some kind of technique and we produced and we got 98% kind of accuracy we claim. And finally, this reviewer accepted the first part. The second part is reactive. Reactive means if someone is asking data, you guess that this fellow can leak the data. Reactive, before passing data to particular requester, you guess that this fellow can leak the data. And that idea, we took it from somehow in my village. My one grandfather, he was very smart. If someone was walking, some new person in village, he always keep eye on him. Oh, why this fellow is coming? Oh, he's not relative of anyone. He was very busy in this kind of job. Any new person comes, we always start investigation. So that technique we apply here. If any new user is asking the data, we apply their behavior with machine learning. We apply quantum machine learning to analyze his behavior. And then finally we take the decision, oh, this fellow can leak the data. That one we call proactive. And luckily we got the publication, we convinced these are the summary part. So this is the first part of our one method. In this case, it was, I think, 4 years back, very well established carrying out. Sometimes कुछ चीज पुराना होता है तो अच्छा लगता है, it's not nothing new. It's old basically. So in this what happened, for example, you want to share some data in our local machine. I think better I check the time also. So yeah, stop, right? Okay. So these just I'm showing the results. So our improvement is up to 103%, and then finally we got this. So I want to highlight this paper. It's the, I think, number 2 paper in our field. The first one is Nature Electronics. The second one is this Impact Package 24. And I think maybe within a couple of weeks we are going to get the result of this paper. Rest is so. This work was the first work which we did in this area in 2020, and we are the first person to prove that data can be leaker can be identified, and we applied statistical analysis, and then we applied some kind of quantum concept. So this quantum-based malicious user, in this case, We apply quantum concept, and very interestingly, you can see to whom will be the case. Green color is our method, and to whom we guess basically that fellow leave the data. Rest other methods they didn't do, but we applied SVM, support vector machine, random classifier, QNN, all these recent latest methods we applied, and we apply our method also. But quantum and method was proposed by us, then we saw that it is very close to this. And another method is this, which we are working. So my last slide is outcome. I don't want here to show the work. The one slide is very important, which everyone encouraged, is appreciated, which I want to show. IIT के सर आए हैं तो इनके सामने दिखाऊंगा. So why cloud will never die? The reason we generated. The first is, if you go for top 5 research area in cloud computer science currently, India and throughout the world, they are basically this. Top 5 research area. आप सर्च करके देख लेना. Everyone is using cloud environment. Without that, you cannot. Therefore, cloud will never die. This one, these are basically they use, but they have alternative. If they don't want to use, okay, no problem. You don't want to use, you buy more supercomputer and run your computer. Never mind. You can pay the money. You don't want to rent, okay. I want to use aeroplane. I have to pay 5,000 rupees. I go Delhi. Okay. I have money. I don't want to pay. मैंने flight ही खरीद लिया. I have money. I bought the flight. No problem. It's okay. They are like this. But another is to save capital and maximize revenue. But another point is some technology like IoT, Internet of Things, where we have a small sensor. You have very small sensor in your watch. You can't expect that watch can be a supercomputer. 25 kilo का तो watch नहीं लगाओगे ना. That is IoT. And whenever we go for Internet of Things, forced to use cloud environment because they generate the data and they process data somewhere else. Whenever we are talking about cyber physical system and all the same concept, they don't have processing capabilities, and for that they have to use cloud environment. Therefore, I always say that cloud will never die. So this one I have to show to my friend also, don't worry. So the extension of the cloud is edge computing, serverless computing is moving now. Serverless computing is very, very popular. So whatever concept you have to the cloud, बस उसको serverless में लेके चले जाओ. Therefore, I always say that knowledge is permanent, technology is different. So like, the first time when the Boolean algebra was given in 16th century by George Boole, all the 0 plus 0 is 1, 1 plus 1 was 1 only. उसके पहले लोग 2 पढ़ते थे, 1 plus 1 is 2. But 1 plus 1 was 1. People surprised 16th century, and after 350 years, Cloud Shannon first developed electrical circuit. Or parallel and series with it, people saw the light. But this is that. So they realize, no, this is Boolean algebra. So still I feel I'm very, very confident about this. Just the things, that's all from my side. And please don't ask the question because I have to catch my flight.
Thank you so much for your presentation, sir.